Uh, Let me share my desktop. So today I'm going to discuss um, some R implementation of hierarchical regression model. So first implementation is the implementation of um, that Poisson-Gamma model that we have discussed. That was a simple give sampler implementation. So let me quickly explain you. So this is actually the data part. There were 10 pumps and each pumps kind of failure, and how many failures happen and what are the time frame when this happens. So that was the like within 94 time units there were 5 failures, within 16 time units there were 1 failure, there are 63 time units, within that there were 5 failures. So that was the kind of thing. So if you read them and R bind them, then this is your data set. Okay, so kind of, and then we wrote a GIP sampler, and that GIP sampler, it's actually a function. So from line 6 to 28, so line 6 to 27 is the GIPS function. If I click on this thing, you can see the extended version of the GIPS function. And then I'm calling it this GIPS function here and the return, whatever this function will return, will be put into the posteriors, and then you can estimate and draws and everything you can do. So the GIF sampler effectively first it writes some built-in function for updating lambdas. It writes the GIF sampler for updating betas, and then it runs the simulation in iteration. Sorry about that. In iteration, the way it runs is basically first it's update the lambda. Now this lambda, current lambda goes in here. Rest of the things are same, and then it updates the beta. And so this is how it keeps doing it. And lambdas, there are 10 lambdas, remember that. So the way this lambda update is written, it will simulate effectively 10 lambdas. Why? Because you see, when I'm doing the lambda update, what I'm doing, I'm saying that R gamma length of Y. So sample size is the length, that how many samples you will generate. So there are 10 points. For each points, 10 lambdas are getting simulated. So these 10 lambdas will be simulated for given Y plus alpha and T plus beta. Now alpha is being considered as known, and so all you have to give update the beta, and beta is updated as a, again, posterior gamma was, beta is a closed form. So again it is just simply simulated one beta given the the updated parameters of A and B, and that is what is being done, and it is being returned. And here it is basically saying that if number of iteration is greater than burn-in, then you put it into the, you store it basically. But if it is less than burn-in, then you don't need to store. So if you run this and then you run the posterior thing, it's already simulated. Just a structure, posterior. So you can see that lambda, there were two objects. One is the lambda draws, another is the beta draws. In the lambda draws, there are 10,000 simulated values are there, and with the 10, there are 10, 1 to 10 pumps. For each pumps, uh, one simulated values will be there, and for each iteration, one beta draws will be there. So this is the typical thing. So it will be like posterior dollar lambda draws. If I just say head, I just say 1, H2, 3. So you can see the 10 for each lambdas, it is being drawn accordingly. So then you do the posterior means. These are the posterior means, and these are the posterior beta. This is the posterior beta. And then within, these are the 25%. So basically, I'm saying that if I believe that these lambdas are coming from hyper gamma distribution with parameter a equal to 1.8 and shape equal to 1.8 and scale equal to 2.4, if this is what we believe, then its 95% confidence interval is this. And you see the first lambda value is outside the range. So the first pump is sort of outlier. It is failing too quickly, perhaps, compared to the, and rest of the pumps are somewhat, some sort of in the range. So you can identify an outlier in this way. Next, we will start discussing the dynamic pricing with hierarchical regression. And the first thing is we are going to use two packages. One is Bayes-M, another is the MCMC pack. Okay. Okay, sorry. And then here is the cheese dataset I'm calling. And the cheese dataset has four variables. One is the retailer, another is the volume, then display activity is the third column, how much display activity is being done, and the price per unit. So if you do question mark cheese, so here it is given. So panel data with the cells volume for a package of board and slice cheese. So board and slice cheese, perhaps, I don't know if you have seen it. If you go to the, say, so that's how the board and slice cheese actually looks like. Okay. So this board and slice cheese measure, so these are display activity and the price, and so retailer, a list of 88 retailers, volume is unit sales, how many pack of cheese are being sold. So 21,374 in 1 week they sold. And this is the 2.5784 is the unit price, one unit 2.57, and they sold 21,000 unit. Where it is? Los Angeles Lucky. Lucky is a super chain in Los Angeles. So Ralph's is another super chain in Los Angeles. Okay, so this is the source of the Macula and Rosie book, actually a paper journal of in the JASA they put it. So account level modeling for trade promotions. So what I'm going to do, I'm going to use this thing. The first thing I'm going to do is retailers. Just extract the retailers. So these are the retailers, 88 exact retailers that we have. Okay. Albany, New York, Price Choppers, Atlanta, Kroger Company. These are all, this Price Chopper is a big name super chain. Kroger is another, Giant Food, Safeway, Super Fresh. And these are the, Albany is a place. Balti Wash is basically, Balti is a name of the town and Wash is the state of Washington. Okay. So in reg is the second, this line, in reg is the number of retailer that we have is 88. Now what we are going to do, we are going to fit a simple ordinary least square method. In the ordinary least square method, first order, so there will be 88 ordinary least square method we will be fitting. Okay. So one thing you can do is plot, say, cheese dollar price, comma, cheese dollar volume. So this is how we are seeing the data. Now, in this way, this is directly, I'm just plotting the price on the x-axis and volume on the y-axis. Now, instead of that, if I just say price in the log scale and volume on the log scale. So you can see now there is some sort of negative behavior. So previously there was probably this kind of behavior was there, very nonlinear logarithmic behavior, but it's difficult to, actually identify. But if you look into this thing, even if it looks like sort of a clustered, almost no correlation, but you can see that somewhat, if the price is 1 and above, then on average the volume is here. But if it is below 1, then the average demand is here, right? Most of the demand is here. So it's indicative that there is a negative relationship between price and volume when they are in log scale. So they are log linear. The demand and volume have a log linear relationship. But what is important, we will see that if you just take, say, any of the two company, say, which is a bit far, maybe one is small place like one could be a big place like Los Angeles, another could be a small place like Charlotte, North Carolina, maybe Harris Teeter, Charlotte, Harris Teeter, comparatively small town, small city than Los Angeles or Houston. And if you plot them, then you will see the one group is here, another group is here. Okay. And you naturally, you don't want a single linear regression model, regression model for everybody, because that will not neither satisfy this group nor satisfy this group. So I think what you can do is, let me just motivate, in order to motivate you, what I can do, I can create a small database. So just let's take a small, say Albany. Albany is really small place. Cheese Albany equals to cheese, then cheese retailer. Okay. So let me do this. Let me clear this thing. First thing is this color. Let me put a different color. Then it will be easy for everybody. So now first let me put a sky blue color on the entire thing. So this is my entire data set. Now what I'm going to do, I'm going to make a small sub data set with the Albany. So if you put, say, dimension of this, so there are 61 weeks of observation. So in fact, if I just go to the environment, and then you see there are 61. These are all Albany price chopper. Okay. So what I'm going to do, I already have plotted this. So I don't want to do, I want to make a overlay plot on that. So what I will do, I'll just say points in log scale, but this will be from cheese Albany dollar, say price, and log scale cheese Albany dollar volume PPCH equal to 20, but color is red. Now if I put this, now you can see these points are Albany, representing Albany. Okay. Albany, New York. It's a comparatively smaller town. Now, if I take, say, a slightly larger town, and clearly I can see that there is some sort of negative behavior in log scale. Now, if you say, let me see what we have. Slightly one, big one, maybe Los Angeles Lucky. Okay, this guy. But what I will do, I will just say cheese instead of Albany, I will say LA. And instead of Albany rice jumper, also this. So let me run this. Now, cheese LA also has about 61 observations. You can see I create another subset, and this one, instead of Albany, I'll just put here and just put here. And instead of red, I would say blue, or already blue is there, maybe purple. or black. Okay. So now you see it's a completely different grouping. Okay. Now what will happen if I just fit one data, one line, the line will pass through here for the entire country. It will do a disservice to this Albany retailer, and this will disservice to this guy because it will make a offer which does not suits to either. So I have to have a fit, I have to fit a model, one for separate for Albany, LA, Los Angeles. Also, I have to fit a separate model for the Albany. Okay, so this is the motivation for, but at the same time, we do understand that they are part of a bigger picture. So that is where the whole story comes in of hierarchical regression model. So we don't want to mix the bigger picture as well. So if you want just brute force separate model, what you can do is you just create a, here I have created a matrix, one of 88 rows, 88 rows and 3 columns. The first column will be the coefficient for intercept. Second column will be the coefficient for display activity. And the third column will be the coefficient for price in log. Okay. And then we are going to estimate the OLS. So what I'm doing in this loop, I'll tell you. First, it will take the retailer and it will create a filter. Between that filter, then that filter will be applied in cheese, and then a small x will be created. X will have 3 columns. One will be the first will be the for the intercept, then this display activity, and then price filter. Log price for this filter, which is for this particular ith retailer. And then given y and x, we will fit a simple linear regression model using OLS method. We will extract the coefficient and put it into the ith row of the thing. Okay. So this is the idea. So this is what we are going to do. Let us do that. It's done. Put the thing also. So actually, let me just. Now it is so 88 rows. For each of them, we got a intercept, display activity, and the log price negative because we have a negative relationship. But the problem is for Boston Stop and Shop, we got a display activity for which it is NA. So not only that, Hartford Stop and Shop also display activity is NA. There must be some issues. We'll check it out. So for Stop and Shop, we're getting this thing. So how can we solve this? Let us check it out, why it is getting cheese. Dollar retailer. See, the display activity in Stop and Shop was always 0. There was no, they never did any display activity in here. So as a result, it did not able to, it was always constant. So they did not able to estimate the coefficient for display activity. So that's why they just simple linear regression model simply dropped that column and fit the models and provided NA for that. Okay, so that is the problem with the OLS. Then what I did, basically data, remember that this regression data was modeled as a least y equal to y and x equal to x. So, and then that least has gone as data. And then simulation size we chose as a 21,000 and burn-in 1,000. And then MCMC parameter is this, fit a SID. And then from the Bayesian package, I'm calling the hierarchical linear model. You have to provide the data, main data, and the MCMC parameters. So let me just run it. It takes about 3 seconds to run the entire simulation. The first thing what we do is it was storing out. So we will see what is there in the out. Structure of out. So a lot of things it being given, but main thing is our beta draw and tau draw. So beta is basically my coefficient. So let us first extract the beta draws and then we will see. So first thing I have done is, so beta draws is basically, it's a 3-dimension array is being supplied. 88, 1:88, the first index is for the 88 retailer. Then for the coefficient, 3 coefficient intercept, 1 coefficient for intercept and 1 coefficient for display activity, and the third coefficient for log price. And then 21,000 simulation on the third index. So what I wanted, I want the first, when I'm basically saying that the first one is you leave it. So that means all 88 retailer I'm taking up, and 1 stands for the intercept, and then burning to simulation size. I don't want all 21,000. I want burning to simulation size. So to run it, and then I'm saying that, all right, you apply on the beta draw 1 mean, and then you round it off to 2 decimal place. So that will give you all the 88 intercepts. Similarly, you do it for the display activity and the rise. Then I computed the beta for all the retailer, and that is what it gives me. Now, if you look at one thing, you will notice there is no NA. So where was that Stop and Shop, Boston Stop and Shop? It did able to estimate the coefficient. So did able to do that because you remember that what we are doing, we're saying the beta I is a coefficient which is a function of a simulation from a, so basically it is drawing the strength from the other data points. Similarly, if you go to the Stop and Shop at, I think, Hartford Stop and Shop, it did able to estimate, and it is somewhere in the 1.16. Most likely it will be near average of all the estimates. But if you actually, my guess is it will be very close to the average of the beta retailer. So if you take the average of that, is 1. 0.99 means 1, near 1. So, and what we found that the ones OLS which cannot estimate by the OLS method or simple standalone method, one for that, I think it was first Hartford Stop and Shop was 1.16, and I think Boston Stop and Shop it was 1.09. So for both the cases it was close to 1. It was not, but still it did able to recover the thing. So on the also what I can do is beta LS is the was my estimated OLS estimated coefficient of the OLS. So what I can do, we can compare them next to each other also. Okay, so what I'll do that plot beta dot ls. Actually, let me just do this. Actually, this is a matrix plot because okay, let me just plot the say 1 H2 2. So intercept and display activity is somewhere in the range of, you see, intercept is in the range of 6 to something and display is in the range of 0 to 25. Whereas head of beta underscore retailer, if you just say first is intercept, display activity, and price. And then plot beta retailer 1H to 22. So in oh, it has to be 2H to 3 because the first thing, I think, yeah. So the first one was, yeah. So this was the OLS estimates, and this was the hierarchical Bayes estimates, and the coefficients are somewhere in the range of -0.5 to 2.5. So if the coefficient is too large, here the coefficient is too large, to be honest. And if the coefficient is too large, that means basically even in a small change in the display activity will have to have 25 times of 1 unit change in the display activity will have 25 times change in the cells effect, and we do know that doesn't make sense. Whereas if you go to the display activity in the coefficient of estimated by hierarchical Bayes model, the display activity coefficient for display activity is somewhere in the range of -0.5 to 2.5, which probably makes sense because if I say that, okay, it is 1.5 coefficient for a retailer is 1.5. So that means 1 unit change in the display activity will result a 1.5 unit change in the cells. And that probably something people will buy into. But, and then this plot, it tells us that, so this is a plot basically Let me just explain you a little bit. On the x-axis, we are estimating the display activity of the least squared estimates of coefficients or the display activity. And this is the posterior mean of the coefficient for display activity, for the coefficient for the display activity. And you see the coefficient for display activity somewhere in the range of negative 0.5 to 2.5 as discussed. And when we use the display activity, first of all, there were two store for which we cannot even estimate the display activity. And then there are some store for which the coefficient are very unreliable, like at least definitely 1, 2, 3, 4, 4 stores for which display activity is very unreliable. So like 10, 15, 25 plus, clearly it does not make sense, because basically if for this store, I'm saying if I do a display activity here, 1 unit, if I just spend $1 in this activity in this particular store, it will give me 15, the volume will go up by 15 times. I mean, of course, that does not make sense. But the same store here, probably if you, its coefficient is near about one, little bit higher, 1.2 or 1.3. This store, it was is being within the some sort of believable range. So this is so two things we are seeing. One is OLS estimates most of the time do good job, but OLS estimate is also very highly prone to leverage some of, leverage some highly prone to the noise. Bayes estimates, on the other hand, is helping us to get rid of this additional noise, and it's smoothen out, and it cuts a balance between local and the global thing. So like if you look into this example, so, or the plot that we did for the cheese, the overall thing, like this one, and when this is the entire data set, and then if I have to do a plot for this guy and plot for this guy, so naturally, if I'm just making an OLS estimate based on these many points, there could be a possibility that it weirds very weirdly. But Bayesian hierarchical model, what happens that the coefficient of these data points are actually will be viewed as a part of a random generation from the entire of a coefficient distributions, which is a part of the entire generation or entire data population. So in that way, there will be a balance will be struck. Okay. Any questions so far?
So can we have a look of the plot of the one where display was really high? So that
This
we
one?
can, so we saw that for one of them, the OLS estimate had a really, for a few of
Correct.
them, it had a really high estimate for the display coefficient. Yeah. Can we have a
This one.
look at that?
Yeah.
I mean, in the as a scatter plot, the way we have for volume and price, can we have like a display and volume for
Acha.
that particular retailer?
Intersect. Acha, volume and okay. So I have to just check it out. So let me just. So there might be retailer. Okay. Just a minute. Retailer.ls. Let me just. So you have to figure out who is that guy who has a very high display activity effect. Yeah. This is New York world worms. Okay, and P, I think there is one with 25 or something. Yeah, so Boston Shaw's. Okay, all right. So let us draw that guy as well. So I will say BA Shaw's. Yes.
So before looking at the plot, I guess the guess would be that there are some outliers that
Correct.
skew the
Possible.
system.
Yes. Yes. Let us see. Highly possible, actually. Maybe we will put a orange there or something like that. All right. Let us draw that. First, I will draw the plot of the entire population.
I think the problem is that we're doing price, but this was a high question for display, right? So we'll have to.
Right. Yeah, I'll do that. I'll do that. I just want to do the first thing so that we will have a. So all the price for this guy is somewhat in one place. Okay. Price to volume activity. Do you see that? And then I'll talk about. So all the. So that makes it, I think, troublesome probably. Display activities. All the price is the variability in the price is almost uh, null. And now if we just do it for the display activity, then it will be much more clear. So let me just, so this is literally called exploratory data analysis for price to volume. Similarly, we'll do exploratory data analysis from, say, display to volume. Okay, so now I'll just, first thing I will do is instead of price, we'll say display activity. Let us draw them. In fact, I don't need log because generally we don't want to, we are not doing it in for log activity. Okay. So this is what we have here. Okay. And then uh, then what we are doing, we want cheese to Albany. We will say that instead of price, you just give me the display. For Albany, so this is how the display activity has happened. So you can see that as the display activity increases, they have a tendency to have a higher volume of cells. Okay. Whereas, so display activity does have an effect on cells. Same, let me just do it with Los Angeles. Okay. So choose with display activity. So all the, that is where all the display activity here. So very little, but still overall this cell is high. But whenever display activity is slightly higher, their volume goes up. I mean, we can clearly see, let me just elaborate it. So we can still see that these are two red ones are the one retailer and the black one is the LA. This is the Albany. And clearly we can see the display activity as little bit increases, their volume has gone up. Okay. So it does have an effect. And then finally, we want BA Shaw's where all the trouble started actually. So I will just put it into the display. See, the display activity is actually there is no display activity, all zeros. 1. Okay. So all 0 and then there was 1 display activity maybe. And that resulted a very, so mean is here for this part and then 1 or 2 points are here, and that's created a sharp OLS estimates, very sharp kind of thing. I think 1 or 2, let us just look into the data for Chase BSO. That is what has happened. Yeah, so most of them are 0. Most of them are 0. There were 2 data points where some display activity has happened, and that resulted probably a little bit of increase in the cells, and that resulted the all problem starts there. Okay, clear? So little bit of tweak in the data, little bit of weird behavior, it would make the OLS estimator highly, or simple likelihood estimator highly unreliable. And that is why the Bayesian solution, remember that any Bayesian solution is effectively some sort of regularization. Okay, so these kind of unreliable estimates becomes much more reliable, regularized estimates, and so that is why we put so much effort to learn Bayesian data analysis. Okay, guys, are you with me? Anybody have any other questions? That was a good exercise. Yeah.
This is kind of beautiful in the sense that each of the, if we did OLS for each one, we would get misled in the sense that we just saw.
Correct.
And if you look at the overall picture, we'd still get misled thinking there is no correlation at all.
Correct.
So the hierarchy still gets just the right sweet spot
balance. Yes.
Yeah.
Yes. This is really hands-on. That's why the hands-on is much more, gives us much more. That's my experience, that how much theory you do doesn't matter. Once you do the hands-on, then theory and the perspective comes into the play. I mean, very clear that why the things are working and why not, and that helps actually. So any questions, any thoughts on this? So what I'll do, I'll going to assign the second assignment, which is going to be a little bit bigger. Okay. Basically, I will share the data with you on COVID-19, and what I would request you, what I will ask you to do, fit hierarchical regression model on these COVID-19 data. I'll explain you in the assignment what to do, what are the things going wrong. I mean, what shouldn't do, what kind of models you try, and all these things. But it will be, I think it will be fun to, play around with it. Okay. Try it out. That I'll try to assign it by today. Okay. So that, and you start working on it, I'll give you as much time as you need, but I think It will be also the very current thing, still live going on. Every day you will see the data is getting updated. So, and also whatever you just learning this hierarchical regression model, you will be able to apply and get a feel of what is going on. So yeah, I think that will be really cool stuff to work on. And I want you to, and then you can do it on state by state basis or the city by basis. So whatever you feel correct. So that will be fun things to do, I think. Any other question? Let me see anything. I will, there is still a lot of the code is still uh, need to be discussed, but I think but before I explain the other thing, I just want to take a pause here and discuss it with you. If you don't have a question, let us then again discuss the
Yeah.
rest of, yeah, okay.
Uh, so is there a way to test if we pick the right hierarchy or something like that?
Good question. My experience is first you pick the uh, data model. Okay. What is the right data model for the problem at your hand? Um, Once you have the data model, like when I'm saying the data model means the model here we are, what is our target variable, dependent variable? Here we are modeling volume. So we decided, all right, uh, that means log of volume is the thing, something I want to model. So some sort of regression is there. And then you think of, okay, is there a natural hierarchy there? And how do you do that? Think of like, okay, here it was, that is the important part. The natural hierarchy for me will be, okay, is there a geography wise hierarchy or state wise hierarchy? So, or, retailer wise hierarchy. And then what you do is think of, do some plot the way we did and say that, think of like, okay, if there is a sort of a natural clustering is happening, okay, uh, doing this overlay scatter plot will help you to understand, yes, looks like there is a natural clustering is happening. And for each cluster, you want to have a separate regression model, but also you want to stitch it to them. If you think of, you have say for us, we have 26 states. Suppose I want to fit a regression model on the number of cases. Okay. So the number of cases as a function of something, positivity rate or something. Okay. Now, number of cases, if is a log number of cases I want to model. It's okay, fine. If the log number of cases that you want to model, then as a but we do know it is behaving differently in Maharashtra and Tamil Nadu. I mean, inherently we do know that. So I have to have a separate regression model for uh, Maharashtra. I have to have a separate regression model for Tamil Nadu. But inherently, we do also know that these two states, even if they are very big states, they're part of the greater India. So they have some sort of commonality which might be different from Europe or Australia or United States, so or Latin America. So what we have to do is some sort of these things. So the coefficient that we will get from Maharashtra and the coefficients that we get for the Tamil Nadu, they should be part of a bigger distribution. They will have their own distribution, these coefficients. And that distribution is the normal. Say, suppose I say, okay, these coefficients are coming from another distributions, and we can think of, okay, that distribution is actually the distribution for India. So if this kind of natural thinking is coming, so then hierarchical regression models sort of falls into the natural places. Okay, so that is the idea. So for typically that is easier way to think about it. Now, suppose you want to model now, okay, numbers and the number of cases are coming in thousands, okay, 10,000, 15,000, 20,000. So if you assume a log of the number of cases following some, I can just do a simple regression model. But if you want to model the early phase of the epidemic, last year, February, March, April, when the cases were coming in like 10, 15, 20, at that time, if you just fit a simple regression model, probably it is not a good thing, because each state is having only 1 to 4 or 5 cases. All over India, it was having only 50, 60 cases a day, right? So what you do with this? At that time, probably a Poisson regression is correct. But in the Poisson regression, so you will think like, okay, number of cases are coming following Poisson, but then rate is some log of rate equal to some beta times X kind of thing, some, but in the beta, again, still you want to model beta for Maharashtra separately, beta for, Tamil Nadu separately, and then you want to have this beta to be part of this big, distribution, which represents India. So if you can come up with this kind of natural argument, natural thinking, the model becomes sort of a, naturally explainable to the bigger community. So that is where these things works very helpful, turns out to be very helpful.
I see. So I have 3 follow-up questions, but I don't know if we have.
Sure.
Do we have time?
Yeah,
Okay.
we do.
Yeah, so the first thing that comes to mind is, for example, if like the COVID example, like one natural hierarchy here would be like latitude, which one might not think of.
Correct.
So if there's like overlap in our possible candidates for the right hierarchy, is that hard to model, or is that just like straight up mixing of the coefficients or something?
You want latitude, longitude to be part of the game?
Yeah, longitude maybe not so much. Latitude I'm thinking because temperature would probably dictate trends.
So you want to model temperature as a function, proxy for latitude?
Yeah, I mean, either thing, it wouldn't really matter. But yeah, I'm just thinking like, so instead of geographical regions, like just countries or something, if we have like
based is if you
have
want
like a
to model
crossing hierarchy.
So if you have the temperature in your model, if you have the temperature data, it is better to model temperature as a part of it instead of latitude. Because why I'm saying so, because in the same latitude, you will see a lot of variation. Say in the Bombay, you will see one kind of variation, but in the same latitude from the Bombay, you move towards the eastward, in the middle of the country, you will find a very different behavior. And for the COVID, what I realized over the period of time, COVID happens always. COVID is a urban disease, means where the density is high, it will spread faster. You will see Madhya Pradesh, Chhattisgarh, there is also it is spreading, but the rate of the spread is much less because the density is much less. Okay. Whereas wherever density is the most important factor in this whole scenario. And of course, other things are there, the people behavior and all these things. So that is why geography turns out to be very important. Latitude or temperature is not going to be, because you see, Europe turns out to be a much more colder place, less. So naturally, initially people thought, okay, it will be much more, I mean, which is probably true, but at the same time, we have seen it even in the very hot country, also the COVID has spread pretty fast. So just weather is not going to affect much in this case, this particular COVID related thing. So
Yeah.
then, yeah,
My question was sort of more abstract. Just this was just an example to say, like, can we have
correct.
something like a hierarchy mixture or something, like where I want to try both hierarchies in some mixed sense or something like that, which is really weird to think about because hierarchies are pretty structured. So
Correct.
that's
Mixture of hierarchy. I mean, mixture distributions of the hierarchy. You are
no,
saying, no.
no, I'm not sure what it would mean, but it seems like if I'm not sure whether latitude is the right way to arrange, like right now we're discussing which one would be the right way to arrange it. And I'm thinking, like, if we didn't have to make that choice and let some statistical
Acha,
method figure it out for us.
not that I know of, it can be done.
I mean, one obvious thing to try would be we could just try all of the things that we think
Correct.
could be candidates and then just go over that.
Yeah,
But
yeah. So basically, see, one way of doing it is you can just simply bring, um, you know, uh, typical ML way of doing it. You put a, dummy variable, what ML people will say, one shot hot encoding, like 1010, wherever you got the, like, for Maharashtra, wherever you got Maharashtra, you got a one. Every other places you put a zero. Then for Tamil Nadu, then for this. But it will only create a intercept effect. But what I want, not only intercept to vary, but I also want my, slope to vary as well. So if you do a one-shot hot encoding, what will happen is your intercept will vary. That will make the slope to, like, your regression line to be up and down. But what will not happen is its uh, slope will not, vary. In the hierarchical regression model, what is happening, not only intercept is going up and down, your slope is also accordingly changing according to the data. So that is one of the advantage of over this, off the shelf ML methods, using, one shot hot encoding.
so that was going to be my second question, which is like if we just use some unsupervised methods to find what the clusters are first to just
Correct.
check that our
Yeah,
hierarchies are.
even that you can do. That you can do first, but yeah, but the problem is once you find the higher clusters also, then I mean, see, unsupervised learning is different. Its main purpose is to find the clusters and identify the clusters. If there are some outlier clusters, you identify them. What is here, the objective is different. Here, my objective is to, what will be my demand? What will be the log volume? I want to demand. If I give this price, offer this price, if I make this kind of display activity, what will be the demand? Okay, if I give a 5% discount, how much, price rise I would expect in the demand curve, in the demand, how much demand it will, so how much revenue it is going to bring in. If you took it the COVID case, suppose you are modeling number of COVID tests, number of COVID cases as a function of number of positivity ratio. If the positivity ratio goes up, then how much, how many cases will go up? If the positivity ratio goes down, how much thing is going down? So this is main purpose of the thing, of the supervised learning. But at the same time, we want to do it in a sense that we do know there is a natural segmentation in my data by the state, by the retailer. And according to those segmentation, I want my model to be adaptive. But if I do simple OLS method, you have already seen what is the problem. If you do ML using putting one-shot hot encoding, it will adjust to the intercept, the bias, but it will not do this kind of behavior. This, intercept will not like slope will not be adjusting to it, to the data. That is where this hierarchical regression model works out very nicely. It can, behaves itself to the data. So two things in order to successful application of hierarchical regression model is, first, you have to identify if there are natural segmentation is there in your data. So the state-wise, so geography and location becomes automatic natural segmentation. Okay, it could be something else also. Like if you're applying it into inside an organization, suppose your KP, you want to model KPI of each employee, key performance indicator, as a function of some of the variables. And naturally, your segmentation at a different level, suppose there are 15 levels of career path, and each level people are working. So you would expect this KPI will behave very differently depending on the level to level. So if you have a natural segmentation, that will be the best thing to have actually for you.
Yeah, so that's really helpful. Let me maybe a quick word about what's my motivation to ask these questions. So looking at this, it just seems like a very powerful tool, hierarchical modeling.
Yeah.
I'm thinking like all of the juicy results will come from unexpected structuring, unexpected hierarchies that aren't obvious. And then sometimes when one discovers that actually the real operating hierarchy here was something non-trivial, then you get really nice results.
Correct.
And anytime I come across a new powerful tool, the first thing I want to check is how do I make sure I don't mislead myself? So that's the kind of motivation behind trying to make sure, like, or trying to figure out if there are like tests for like going outside of the regular hierarchy and seeing if it's still possible.
So that will be okay. All right. So one thing one can do, yeah, I agree. The real crux. So basically, if you have an already existing hierarchy, natural hierarchy, then you can apply this. You can just go ahead and apply this hierarchical regression model. But at the same time, I agree with you. Suppose in your data set, you don't know where is the natural hierarchy lies. So that time you can take a two-step process. In step one, you can apply some kind of clustering methods to identify the clusters, right? And then you say that, okay, I have identified, I have done this segmentation or clustering exercise. I've found that there is a inherent 5 clusters are there. Cluster 1, cluster 2, cluster 3, cluster 4, cluster 5. And I say that, okay, these are the natural hierarchy. I would consider them as natural hierarchy. And let's apply hierarchical regression on these 5 clusters. And then probably it will be much more very effective. It will be much more effective. Right. Yeah. So that will be step 2. But in order to make um, in order to apply, so yes, so you can use a clustering technique to begin with at the data process at the step 1 to identify your hierarchy or the segments of your entire data sets, and then you can apply the, but as a, yeah, so basically what I'm trying to say, that hierarchy becomes natural kind of, is a sort of an input into this hierarchical regression. So that will become a step 2 for you in that case.
Yeah. So, I mean, this obviously is in tension with the point you raised earlier that clustering might not actually give you, like, for example, in the data set we just saw, if we try to cluster it, we would probably might not discover these sorts of trend lines, which are actually very clear when we know that segmenting by retailer actually makes it gives a very clear picture. And it's not clear that these would pop up in clusters. I'm not sure that they would. So yeah, it seems like it would probably be more complex than just like trying to run some. My third question was like maybe sort of unrelated to what we discussed. Actually, it is. So I mean, we are not, so today it was very easy to see what the problem was with the Boston Shaw retailer. But I'm imagining a debate between someone who insists that your hierarchy is bad, that's why you have this prediction, and actually the OLS was the right one. And today it was easy to see that the Bayesian wins. But again, maybe this is the eternal debate of how much priors should affect. Like in the sense, this is like you said, everything is regularized. It's just a regularization thing. So maybe this debate will continue on. But again, just like if there is like a quick test of C in this case, like it's maybe a statistical test. I don't know. That
no, I mean,
in this case the Bayesian wins or something.
Yeah, I mean, if you see it from, I mean, majority of the time, I have seen Bayesian wins, and so if there is a frequentist in the room, and my typical way of saying let them go is, okay, you don't want to call it Bayesian, you call it regularization, so be it. But end of, I mean, that is fine with me. If you want to call it regularizing, penalizing likelihood, whatever name you want to give, you give it. But end of the day, it's a Bayesian solution. I mean, so that is what the way I see it. And another way of looking at it, it's basically you are bringing additional information, and sometimes the information not obvious to you, but effectively it is an effective way to incorporate the structural information into your model. So my structural information is the hierarchy, and I want my intercept and slope to be adjusted according to its natural structure, and that is getting captured nicely in this hierarchical regression model. So, or this Bayesian structure, I think that is where the main the power of the entire thing lies in that.
Yeah.
Also, but typically you will see most of these hierarchical uh, models actually a very successful application of the nice conjugate structure. You will see that they always try to take the advantage of these conjugacies, so that you can if you have this entire nice conjugate structure, then you can simulate the data very easily from the posterior using Gibbs sampler kind of thing. So that is an advantage of having a nice hierarchical structure. So yeah.
Yeah,
So
so it's something
this
like
hierarchical regression is a place where whatever I have taught you in the entire course are basically getting into in one place. It's like I started with the basic likelihood, prior, and conjugate structure. Then I went into the Gibbs sampler and all these things. All these informations actually nicely stitched together and put it into the Bayesian hierarchical models. And that is where it's, and then you will be able to see the strength of this method.
Yeah, what I was thinking about your earlier point, it's sort of like some expert at Boston who's only worked in Boston Shaw is like, when we started doing display, our volume shot up, therefore we should invest a lot in display. But an expert who has worked across stores is like, actually, we know that that's not how it works. It's actually more complicated things.
Correct.
Yeah.
Correct. So that is why I keep saying that you have to be if you are not familiar with all the Bayesian tools and you are just working with the OLS estimate with the LM and off-the-shelf ML estimates, and if the estimates are giving you a bit off the bet, the coefficient estimates are not reliable, then it is better you speak to the domain expert and make whether it makes sense, right? Sometimes just basic exploratory data analysis tells you what is happening. Sometimes it's much more difficult. Yeah. Okay. All right. So there is what I will do today. It is almost 1.5 hours now. So what I'm going to do today, let's not, I'll share this code right away with you. I will also upload this discussion. It was a very nice discussion. And I will assign the assignments. And maybe in next couple of weeks, I mean, maybe Thursday, I'll complete the code, rest of the code. You can just have a look in the code. I actually give as much explanation as possible. But I think this is but definitely Thursday we can finish the discussion on the code, rest of the code. All right, and I'll assign the next assignment. There will be the one with the COVID. Main problem with the second assignment will be the modeling the COVID-19. Okay, so I'll do that. I'll do that by tonight. So I think you will enjoy modeling this, the hierarchical regression and all. Okay, all right. Thank you.
Thank you, sir.